my name is Jeremy. I'm from Uber. So today we're going to talk about the experimentation platform on our team. So first, a quick introduction of Jeremy and Mandie, and also our manager Anirban is also making a lot of contribution to these slides. So first, let's give you an overview of the methodologies we use. So in Uber, we divide our methodologies in two parts. The first one is the randomized experiments, and the second part is the observation study when we cannot run the observation study, randomized experiments. Oh, sorry. So when we look at the randomized experiments, we basically run the random split to generate several groups, and then we run analysis after that. The simplest one is called A/B test, when we only have two groups. So in the randomized experiments, we have two parts. One is classic statistical experiments, meaning that it's like a one-time thing. We run the experiments, we see the results, that's it. The second part is called continuous experiments, meaning that we keep the experiment running when we're collecting data and analyzing at the same time. So in the classic experiments, as you see in the textbook, we have two parts. The first part is called univariate test, which is A/B test, and the multivariate test, which is factorial design, block design, and all those other advanced techniques. So here in Uber, we create a new deck, which is continuous experiments. We allow the customers to use the experiments continuously. So here we have also two parts. One is called heuristic techniques, which is the one we are going to talk about, company sampling, and Mandie is going to cover the power and risk-based stage rollout. The second part is called model-based techniques, which we use machine learning techniques to combine with the traditional statistical experiments. We call it contextual multi-bandit. And also with some AI included, we will also using the reinforcement learning inside. But here we only talk about the multi-bandit, stage rollout, and the contextual multi-bandit in these slides. So for observation studies, which we often use another concept, which is causal inference. So here, causal inference meaning that when we cannot run the randomized experiments, we still hope to understand the correlation and also the causality. Here we have several mathematical forms, which is difference in diff, and synthetic control, multivariate matching, and also some machine learning-based techniques. But this will not be covered in these slides. Just give you a quick overview of all the methodologies we use. So for randomized experiments, as an introduction to these next slides, we hope you to understand that we are running A/B test at the very beginning, which is control and treatment. We want to compare the difference between the two. And in Uber, we have several use cases like product feature. So we are mobile team. So basically, we want to release the new versions. We need to make sure there's no accident, for example, crash rate. And also in the marketing team, we hope to give them different messages to our customers, and we hope to understand which channel or which type of message is the most effective. And the last one is called incentive spend. We always give promos or some discount. So we hope to understand which type of promo can optimize the customer experience, also optimize on our supply hours or rides or the number of drivers. The continuous experiments also have several use cases like content optimization, hyperparameter tuning, spend optimization, and the automated stage rollout. So the number two, hyperparameter tuning, meaning that it's different from the cross-validation as we always use in the machine learning work. So cross-validation is a very good way, but it's always offline. So we take the data out like a batch, and we run the training and the testing and also validation. But here in Uber, many models is online, meaning that we don't have time to put the data off. The data pipeline takes some time. So we hope to make sure that the online results match the offline batch results. So in this case, we use continuous experiments, which allow the real-time training. And the observation study here, we primarily focus on marketplace, and also we have some like marketing channel and some other use cases, but it's very ad hoc. For example, if we want to know like whether a trip is safe or not, we track like two things. One is that whether the driver is following our Uber map. Another one is like driver has their own knowledge of the local situation. They will choose their own preferred route. So we hope to understand which one is is much safer. So in this case, we cannot randomize like, oh, you go to the dangerous route and then you go to the safe route. We cannot do that. So in this case, we have to use an observation study to analyze the difference. So here is a quick introduction to continuous experiments. So we will have like two use cases. So the two use cases is around the topic of modern bandit. So here, the modern bandit is originated from the casino, which we hope to understand which slot machine will give the highest rewards. So here's a page of like a quick overview. Like it's a sequential experiment. It's balanced exploitation and exploration, meaning that we hope to try more if we know this one gives higher rewards, or we just simply invest without getting any rewards. And the key difference between continuous experiments and A/B tests is the purpose. So the purpose of A/B tests is to give a p-value to generate the decision-making criteria. But in the continuous experiments, the modern bandit we hope to give the larger rewards. How do we do that? So A/B test always requires the half-half split, meaning that we can generate the highest power based on statistical theory. But in the multi-bandit, most of the times actually, we give like the higher weights to the better performing groups, and we give lower weights, lower traffic, or lower number of sample sets to the worst group. Here is the case studies in Uber for multi-bandit. First of all, it's like content optimization. We have like Uber credit card email campaigns who, those marketing managers hope to understand which method is most effective. They also hope to maximize the rewards, meaning that maximize the ROI. Number two is the hyperparameter tuning. We primarily work with Uber Eats teams because they run a lot of machine learning algorithms online. And number three is spend optimization, which is primarily focused on like advertising. So Google and Facebook, they have some talks in the multi-bandit. So we'll do the very similar thing, but our use cases are different. We focus on bidding and promo strategy. And number four is automated stage out, which is like monitoring models for the release. And Mandie will cover this part. So here we are starting with the first case study, the one we focus on email campaigns. So I will slow down. So the previous is like quick introduction to the techniques. And from this page, I will talk about the Uber use case. So this is the email we hope to send to the European countries for the new Uber Eats customers. We have the headline, which is the subject line, like welcome to Uber Eats. This is like the structure of the emails, like the headline, the header, CTA. CTA meaning that some hyperlink in the email, and the body of the email. So we focus on the subject lines. Right? The objective is to maximize the click-through rate. So here, I put them in separate buckets. The first one is called topics. The topics around the CRM, the customer relationship management, in Europe, in EMEA. We hope to understand like which email is the best email for our customers to read. Oh, by the way, we focus on the English countries, so all the emails are written in English. And also the modeling part is that we use content sampling to change the allocation of the weights. So for example, day one, from all the 10 treatment groups, they are all equally split, like 10% for each. But in the next day, the allocation may be different. The impact is that the other teams, like the finance team or like the other regions, may also want to use multi-banding. The second part is that we'll keep doing the automation to make sure the engineering pipeline is healthy. So here is a very high-level summary of the comparison between A/B test and multi-banding. So in the A/B test groups, like the separate log 1, 2 until 10, they have the same allocation weights, 10% for each. The business metric is open rate, the number of open emails, and the data collection took about like 8 weeks. And in the multi-banding groups, like you said, the red means that they are not performing very well, so we give them smaller weights. And if they are working good, so we give them higher weights, meaning higher traffic. The results, there are several parts. First of all, is our customers, marketing managers, they care about the open rate. The second one, they care about how many more open emails. And number 3 is that by design, A/B test is supposed to run for 8 weeks to get the p-value. But in multi-banding, we see about 35% of the time we got the results around like 5 or 6 weeks, like 2 weeks of the same time. Here is the best group. So I hope to ask you guys a question. Like I'll give you 3 choices. Like the first one is welcome to Uber Eats. The second one is thank you for signing up. Number 3 is are you ready to order? So which one do you believe is more likely to be clicked on the email? Number 1 is welcome to Uber Eats. It's your hands. The second one is thank you for signing up. That's 1, 2. Okay. Number 3 is are you ready to order? Exactly. Got it. So we have the results that saying that if we have a question mark and we ask the customer to take some action, they are more likely to respond. And when we say like thank you for joining Uber Eats, all those thank you meaning that we are going to end that conversation. We're not going to continue. So this is an insight from the European countries. And in the Brazil and Costa Rica, Latin America, we have a different insight, is that they like the emoji. If we put emoji into the email headline, they are more likely to click on it. And compare European and Latin America. So the key difference is that the Latin American countries, they are not checking emails very often. They like the Android push notification. And in the European countries, the email is more effective. Here is like how we track the allocation week by week. It's a very tense slide, so I will just pass. So the second case study is for the Uber Eats machine learning team. So basically, we hope to help them tune the parameter online. The methodology we use is called contextual multi-banding, which use multi-banding techniques, but also we include the personalized information into the machine learning model. Here this is the slide I put, like stats plus machine learning meaning contextual multi-banding. So like stats means that we are going to run the experiments, and machine learning means that we're not using the traditional way. We put the like the treatments or the blocks or the covariates into the machine learning model, and then we are generating some performance score based on the 2 set of features. And the techniques of optimization we use is called Bayesian optimization, which is like a sample technique. How do we teach the experimenters to collect data? So traditionally, like A/B tests, we split like 50-50, meaning that they may be not correct. If we already know treatment is better than control, some data points is wasting. So here we are going to teach our customers with how many data points we should collect from which group. And this is called active learning if you're interested. Okay, the second case study, I just put like 2 pages. The topic is restaurant ranking. So if you open your Uber Eats app and your friend open it, you will have a different order of the restaurants. And the business problem is that the Uber Eats data science team, they hope to drive more revenue, higher conversion, and higher retention. So we maximize several things. That's why we call multi-objective function. And the modeling part, which are done by the Uber Eats team. The first one is linear programming because it's an optimization problem. The second part is machine learning. So within this linear programming model, there are several metrics that we need to predict it by machine learning models. Here is how we participate. We use the A/B test in the very beginning to help tune the parameters in these two models, and then we figure A/B test takes so long, and A/B test is it's not scalable in terms of the number of treatment groups. So that's why we move to continuous experiments to help them tune the parameters. So eventually, no matter it's online, offline model, we need to use statistical experiments to measure the leak. So here's a quick comparison of the differences between A/B test and our continuous experiments for this case study. Basically, the key points is we hope to generate more and more treatment groups in these experiments, and the A/B test is not scalable. That's the key difference. And the second part is there's no automation between the A/B, so we hope to use the continuous experiments to have the customer to automate the pipeline so that they don't need to spend a lot of time to configure each of the experiments. So that's the two key points. So next is the case study 3. Let's welcome Mandie to cover.
I'm a data scientist working at experimentation platform at Uber, and I'm happy to share one of my project, which is StageOut. Okay. So StageOut is a short name for our monitoring system for monitoring the key business metrics when we wanted to release a new mobile feature. Basically, this whole system does two things. One is monitoring, and the second part is it decides the speed for us of how we can release the feature from exposing this to no audience until we release this feature to all audience. Okay, so I will give the introduction first. So what is a mobile feature? So any code change can be a mobile feature. It can be like either front end that is visible to users, like what you will see on the app, like how you give tips to driver, or how the map is shown on your map. Or it can also be like back end, like things that you are never noticed, like how our back end is doing like matching, and how your co-writer is decided. So all this is called like mobile features. And we, as a mobile company, are like heavily invested to deliver desirable features to all of our customers to make you all happy. And so basically, we are releasing new features like very frequently. And all our hope is that we hope that our feature release could be successful. Basically, like existing users and new users, they update their apps through either like Google Play or iOS App Store, and then like you would still use our app and feel very happy. But things can also like be not that successfully. Like when you upgraded your app, it can happen that your app is showing a crash, and sometimes like some functions are not like showing normally. So that, or like it can also happen that you just simply don't like the feature and you don't want to use it anymore. So in order to just monitor the whole process, we wanted to build a system that can always give us result of how our users are interacting with our new feature, and also help engineers to decide like how to gradually increase the number of people that are interacting with our new feature. Okay. So this is the summary of this problem. Basically, the topic we wanted to solve is we wanted to reliably release our feature within several days, like 1 week or like even longer if it's very important. And the business problem is like, let's think of this as two-sided. If the feature is fine and everybody is happy with the feature, we wanted to know this as soon as possible so that we can launch this feature very quickly and so that more people can interact with this new feature. However, if the feature actually has some problem or like people don't like it, then we wanted to detect this degradation as early as possible so that engineers can start debugging and like we can revert this version to the original version where everybody is happy at. So to solve this problem, we basically modeled this from three parts. The first is how we conducted the daily monitoring. We basically use a technique called sequential test, which enables us to basically conduct comparison between treatment group and control group whenever we even have one new data point. The other two models, the first is power-based or risk-based criteria, and the other part is time series model. These two help us to decide what is the next day percentage of people that can expose to the new feature. So the impact of this project is that now the stage rollout is basically the primary tool for engineers at Uber to release new features. And actually this have helped us to detect many degradations and help us to deliver a reliable feature release process. Okay, so let's start from this Latch Chart. So to give you an example, suppose we wanted to launch feature X for all the users in US on app version 2.0 within 1 week. Then starting from day one, we will gradually increase the percentage of users that we exposed on our new feature. So, and also including the same number of people in control group to make as a comparison. So we start from 1%, and then we gradually increase to 5%, 20%, until the fourth day we have 50% of treatment and 50% of control. And in the whole process, we are monitoring our key business metrics, for example, crash rate. And if nothing degradation is happened or is detected, and if we are reaching the power that we are very confident that going forward no degradation will happen, then we will release our new feature to 100% of total users in this segment. So, like I said, there are two components in our algorithm. The first is how we conducted daily monitoring. There are many metrics, like crash rate is only one example. It can only be like a trip rate or like the supply hour, things like that. And there can be two consequences. One is like actually there is some degradation and we already detected. So if that happened, then we will stop this new feature release and revert everybody to the old feature. And the case two is like no degradation is detected. And this actually means two things. One is that actually in the end, like people will be happy about this new feature, and we just don't have like enough sample size to reach the power to tell that. And the second case is that actually the feature is not that welcome, not that good, but we haven't collected enough statistical samples to say like, oh, we detected the statistical difference. So whichever way we wanted to increase our sample sizes to include more people in our sample and to do the statistical analysis again. But as you see, like there are very two different scenarios. So we don't want to expose too many people if the feature is actually bad. But actually we wanted to include more people if the feature is good. So how we make the rollout decision of what is the percentage of people for the next stage? Basically, we do two steps. The first is we want to calculate the required sample size for the next stage. In Uber, we have tried like two methods. The first is power-based, which is based on sequential testing algorithm. It's a conclusion that we can draw from the power analysis. Or the method two is a risk-based algorithm, which we formulate this as aviation testing algorithm. Basically, we wanted to limit the probability of, let's say, of having 1,000 trips within 1 day, and we wanted to control this probability to be less than 10%. And using that, we can calculate the required sample size for the next day. And then the step is we wanted to know what is the sample size compared to the total sample size for the next day. So basically, we wanted to build a time series analysis to predict how many people will come to our app on the next day. And then we can get a percentage. And following that percentage, we can get this number. Yeah, so this is how our stage loss system has been behaving in Uber. And this is our presentation. We are happy to answer all the questions.
Are there any questions?
I can see now. Yeah. Can you go back to the case study one?
What is your question?
I mean, you're trying to test the different. I mean, the subject line of the page or the email. Yes, my question was like, it looks like you're assuming that the different components of that email are independent, right? Have you ever tried any combinations of the testing?
Yes, we did. So the first one, this is a pilot project. We hope to understand the one key metric, the open rate. So in other projects, we also have like conversion rate and some other retention rate. So we observe several metrics. And to answer your questions, so the combination of the email has to be approved by the legal. So we hope to test the one thing at one time. So here we only test the subject line. In other case, we test the body of the email, but still it's one part. We haven't started the combination of the two or several components in one email. It's going to do kind of the project because it's a very good use case for contextual multi-banding. It's like better for case study too.
I have another question. This is more personal, but like so for example, on the app on my Uber Eats app, for example, there are two restaurants. They are exactly the same, but one is like by the way, it's Hello Chicken, it's fried chicken. And one is like 5 miles away, the other one is 1 mile away. But the app always recommends the 5 mile one. I don't know why, but could you explain me why?
You mean the 5 mile one is always showing up first?
Yeah.
Maybe they have the better conversion because the ranking is ranked by several things. One is your personal preference. The other one is the aggregated results from other customers. This is more like collaborative filter. So, but with your personal information. If you haven't used Uber Eats before, so this is very common because other people may be more likely to click on the second one, the farther one. Thanks.
I know you mentioned randomization experimentation, but we all know that there is a lot of confounding factors we want to control, especially in the real life. So I wonder what is the most critical and common confounding factors you would consider, and if you'd like to share how do you control them.
So the confounding factors we observe a lot. So that will be solved by the contextual multi-banding. So like confounders is some variables in the hidden layers. So for example, the time is a confounder. For example, in the lunch time and in the dinner time, our customer have different behaviors. So in this case, the second case study, we put time into our machine learning model. Like at the dinner time, we analyze the results. It's different from what we have in the lunch time. So basically, we put them into machine learning models. Like I said, it's two sets of features. The first set of features is randomized. It's something we hope to understand. The second part of features is the features that are not randomized, including the confounding.